Okay, so we're continuing in our segue here between um, Laplace transforms and systems of equations. And what I wanted to do in this part was just to look briefly at some parametric equations, some vector fields, and the relationship to differential equations. Okay, so from Calc 3, you might recall the way we wrote a curve in the plane was r of t, right? That was using angle brackets with either x of t, y of t, or x, y, and z. So for example, a curve in the plane, this is a circle in the plane, you could describe that in terms of your parametric equations, k cosine t and k sine t, where k is the fixed radius here. And so the parametric equations are very helpful in describing curves in the plane. Okay, the problem is that mathematicians don't typically use angle brackets for vectors. So later on we're going to change notation a little bit to make it more standard. But I did want to mention that it is possible to differentiate a parametric set of equations. So r prime is x prime y prime. You could also integrate. Um, and so that's just being done component wise. So there's also, you might recall from our exact equations, right? Given a curve in the plane written out this way, f of x, y equals c, kind of like a level curve, we can differentiate using y as a function of x, and so these are partial derivatives, right? So if you differentiate, this is a total derivative here, f sub x plus f sub y times dy over dx equals 0. We could bring the f sub x over, make it minus f sub x, divide by f sub y, and so we can describe dy over dx with a formula, right? So think about going backwards then. You might see dy over dx being some function of x and y, and so that would be corresponding to this representation of a curve in the plane. Okay, we might be able to mix the two together like we did before, where we had, if we have x prime and y prime, right, we can write dy over dx as y prime divided by x prime. Okay, so there's a couple ways of representing the derivative. Now, something similar is a vector field. So a vector field is a vector valued function, which means that it takes in a point and it outputs a vector. Right, so in Calc 3 we typically would write our vector field as p for the p is a function of x and y for the x coordinate of our vector field, and q is the function of x and y. These, where p and q are scalar valued functions, right, or real valued functions. Okay, so therefore f puts in a point and outputs a vector, right? And so p, the function p here, tells you how you're changing in the x coordinate, and q is telling you how you're changing in the y coordinate, right? So you might recognize that's actually a set of differential equations. And so before we get into that, let's just do an example of a vector field. So this is just a real basic, simple vector field. F of xy is minus yx. So what is the vector field? How would we plot such a thing? Well, every point is associated to a vector, so therefore we can just list some points, and then we can write down the associated vectors. And then we can just plot the points, or plot the vectors as emanating from each of those points, right? So at the point 1, 0, we have the vector 0, 1. So at the point 1, 0, we have the vector 0, 1. It's going straight up. And then similarly here at 0, 1, we have a vector negative 1, 0, so it's going backwards. Similarly here 1, 1, that's not 1, 1. That's negative 1, 0. We have 0, negative 1, so it's going down, and so on. Okay, and then at the point 1, 1, that's over here. We're moving in the direction of minus 1, 1, so that's why it's back and up. Okay, and so the graph of all of those arrows is called the direction field, or actually it's a vector field. But it actually is a direction field for some differential equation, right? Because what if I had changed this formulation here? What if I had said x prime is equal to minus y, and y prime is equal to x, right? Then the points in the plane just represent your starting point, and then my differential equation is telling me which direction I'm moving, and so you would get the same thing for the direction field, right? This would be a direction field for x prime equals minus x, y prime equals x. Okay, um, let's see. So that's actually tying the vector field into the parametric equations. So if we have x prime and y prime defined in terms of x and y, right, then the solution to the system is some set of parametric equations x and y that satisfy this relationship. Okay, and so the direction field for that system is, like I was just saying, little f and little g. Okay, so therefore we can write dr over dt in terms of our vector field. And like this says, this is a little bit awkward. Normally we don't write things like this. So let's change the notation slightly. Mathematicians like to write vectors in columns, and so let x of t be x1 of t, x2 of t. So again, whenever you see a column, that's just a vector. Then the system of differential equations is defined as the vector x of t with take the derivative of that, and that's equal to the vector valued function f, whose input is a vector x. Okay, and so x prime and y prime, then you could write out what this means. This is just the derivative, and then this is your vector valued function using x1 and x2 instead of x and y. Okay, so this would be like your little f before and your little g before. Good. Okay, and so this is typically what we see. And so if you were to take classes in differential equations from here, this is typically where those courses would start. We don't look at nth order differential equations because, as we know, any nth order differential equation can be converted into a system of first order. And in fact, if you try to use any kind of numerical solver for differential equations, you'll almost always have to convert it to a system of first order differential equations before you can use the algorithm. Good, so that's a good thing to keep in mind. Here's a few direction fields. I wanted to just take you through a solution to some of these so you can see what the solution actually looks like. So here's the direction field, just a very simple one. You'll notice that the author here is using parentheses for vectors. That's the third way we've seen of looking at a vector today. So that was angle brackets as a column, and now using parentheses. Okay. So this is a very basic direction field. That's x prime equals x, y prime equals y is what we're going to be looking at. Direction field for minus x minus y. That's just the opposite, you'll notice. That's from the first one. And this one just changes the strength of one of the variables. Okay. And so you'll notice that the curves, or you're starting to see some bending going on here. Good. So let's go to 2.21 and just see if we can solve it. X prime equals x and y prime equals y. This is called a decoupled system because x prime does not depend on y and y prime does not depend on x. So therefore these are just two regular first order differential equations that we saw in chapter 2. And so we can just solve them directly. X of t is c1 e to the t, y is c2 e to the t. Notice that if you put in times 0 here, then x of 0 is c1 and y of 0 is c2. So you could write that as x0 and y0 instead of c1 and c2. And then I just factored out the e to the t. Good, so this is the solution to your differential equation. And you'll notice that this is just, if I change the time values, this is just going to be different scalar multiples of this vector. And so the solutions are going to be along the line emanating from the origin in this direction. Okay. And so the second case was almost identical, except you just have a negative sign there. And so this again, think about this as scalar multiples of this vector. But now we're just changing the direction. We're heading towards the origin instead of away from the origin as time progresses. And finally, the last one's a little bit more complicated. but we can still solve it because it's uncoupled. X is the same, Y is slightly different, but you can do a little bit of a trick if you'd like. You can get rid of the time parameter in a parametric system. Remember doing that from Calc 3? So in this case, I can rewrite e to the minus 2t as e to the minus t squared. And the reason to do that is because I can now solve my first equation for e to the minus t. That's x divided by x0. Substitute that in, and now I see that y is actually a parabola. And so if we go back to that graph, you'll see that solution curves are actually parabolas. Solution curves are parabolas in this direction field. So that's kind of interesting. All right, so as one last quick example, a matching, I've got 4 of these in the notes. I would recommend you going through those. Let's just go through one real quick. Do you see F1 between these two graphs? Here's a hint, it's this one. Notice that the x-coordinate is always minus 1/2. That means you're always moving backwards, 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 backwards. And this negative x means that in the right side of the graph you're moving down, and in the left side of the graph you're moving up. Good. And so this graph is the graph of F1. Good, so try out the other ones. We're out of time now for the remainder. Um, next video we'll actually be getting back into the book. Okay, see you then.